Yeah, please pay attention to this lecture. You will get some tricky questions in the next TBL. Okay, so study hard. I'm just warning you, okay? And I want you all to get a complete, like a full mark, okay? So this is why. Okay, should we start? Okay, so let's start. Bismillah ar-Rahman ar-Rahim. So today's topic is on the action potential, which we keep mentioning, right? And so what is an action potential? An action potential is basically a rapid sequence of changes in the voltage across a membrane, which is the change in the membrane potential, okay? So this is caused by changes in the permeability and concentrations of ions across the membrane, as you learned. And the action potential is basically the language of some of the excitable cells, like neurons. This is how neurons communicate with each other, is via the generation of action potential that travels along the neuron to release neurotransmitters to, communicate with the next neuron, okay? So as you can see here, this neuron is the sending neuron, and this big one here is the receiving neuron, okay? So the sending neuron will communicate with the receiving neuron via, this cellular location. So this is the synapse, presynapse, and this is the dendrite of the receiving neuron, okay? So what happens here is basically the following. So this neuron, the sending neuron, okay, the depolarization of the sending neuron here, so the action potential will travel, down the axon to reach the axon terminal of the sending neuron. And so the sending neuron, the action potential will trigger the release of these neurotransmitters, we call them, okay? So these are chemical mediators, okay? So will be released in the cleft here. And so these neurotransmitters will bind to ligand-gated ion channels. So what's in here in the dendrites are ligand-gated ion channels, not voltage-gated channels. They are ligand-gated ion channels. An example of this is when the sending neuron releases glutamate. Glutamate will bind to an MDA receptor, and the MDA receptor would open and will allow the influx of sodium to the inside, okay? And so when sodium is getting to the inside, what will be generated is a graded potential. Not an action potential yet, it's only a graded potential, which is very small, and the signal is very small, okay? And so what happens in here is basically in the dendrites and in the cell body is the generation of a graded potential, which if it's high enough, if the graded potential is large enough to reach this area here, which is called the axon hillock, okay? If the graded potential was high enough to depolarize, you know what depolarize mean, right? Yeah, to depolarize the axon hillock, okay, to bring the membrane at that particular location to threshold for the voltage-gated sodium channels to open, then we would have a full-blown action potential, okay? So graded potential is generated in the dendrites, okay? Whereas the action potential is mainly generated or initiated at the axon hillock. Then it will travel down the axon to reach the axon terminal, where it will trigger the release of neurotransmitters, okay? So what is the difference between graded potential and an action potential? One of the differences is that the graded potential is short as a signal, okay? And also it can accumulate, okay, where, it can somate, okay, in order to bring the axon hillock to depolarize, to the threshold, okay? And an graded potential can be excitatory and it can be inhibitory as well. What do we mean by that? Excitatory is when we are depolarizing the neuron via the entry of sodium, right? When sodium enter into the cell, this will make the cell less negative, right? So we are depolarizing the neuron, and so there is the chance that this neuron will generate an action potential. So it can be excitatory, and it can be inhibitory by taking the neuron away from the membrane, away from the threshold. And this can be via the entry of chloride, okay? So chloride, for example, as an example of excitatory is when the glutamate, okay, the neurotransmitter glutamate binding to the MDA receptor and allowing sodium or calcium to get into the cell. This is an excitatory graded potential. While GABA binding to a GABAergic receptor would allow chloride to enter the cell. This will make the membrane an even more negative, right? And so this will hyperpolarize the neuron, and so this type of signal is called inhibitory graded potential. Is that all clear? All clear? Okay. So this is the graded potential. So when there is a stimulus, okay, so here we have a stimulus, and if the stimulus was not big, okay, so it's not big, and it has, depolarized the receiving neuron, it created some graded potential, but the graded potential that was created is not big enough to reach the trigger zone, the axon hillock. So this stimulus or this graded potential would not, induce the generation of an action potential. And so this type of graded potential is a sub-threshold graded potential, because this graded potential did not result in the generation of an action potential at the axon hillock. While in this case here, this one is a supra-threshold graded potential. So there is a large stimulus that resulted in a release of many excitatory neurotransmitters, opening of many ligand-gated ion channels. This resulted in a larger graded potential, which eventually reached the axon hillock and resulted in the depolarization of this area to the threshold and opening the voltage-gated ion channels, resulting in the generation of the action potential, okay? Is this all clear? Clear? Okay, good. And so why the graded potential loses its strength when it reaches the axon hillock is because of the leakiness of the ions in the cell body, okay? So where basically the graded potential will decay as it travels away from the site of origin. And so this decay in the signal has been given a name, which is the length constant. So the length constant basically describes the distance, okay, by which the graded potential would be decreased to 37% of its original amplitude, okay? So you can see here, this is where the graded potential was, initiated. And so by the time it depolarized the rest of the cell body, it loses its strength. And so the distance by which the graded potential will be losing 37%, or by losing or decreased to a 37% of its amplitude, this is called the length constant. And so the larger the length constant, okay, the more likely that the graded potential will result in an action potential, okay? Yep. Sorry? So the length constant is the distance by which it will decrease to a 37% of its amplitude. So what does this mean is that the larger the distance before it loses 37% of its strength, then the likelihood it will induce an action potential. You see what I mean? So because, for example, in neurons where there is high resistance for, against leakiness of the ions, so some neurons, because, of the size of the cell body, whether it's small or large, they would have a higher resistance against the leakiness of the ions. And so the graded potential will travel, a longer distance before it loses 37% of its amplitude. And so it will reaches the axon hill lock, and will induce an action potential. So this is called the length constant. So the larger the length constant, the higher the likelihood that the graded potential will result in an action potential. Yep. Decreased to 30, the distance by which, when it's, the distance by which it decreased to 37% of its amplitude, okay? Sorry? No, it comes to 37, yeah. It decreased to 37 of its original amplitude, okay? Is this all clear? So once the graded potential is high enough, okay, and to depolarize the axon hill lock, to bring this particular, the membrane in this particular location to the threshold, it will result in the generation of the action potential. And what is, special about this location? Anyone has an idea what's special about this location? Sorry? Non-myelinated? No. What's special about the axon hill lock? Why it in that particular location, when it's depolarized to the threshold, it will result in an action potential, yes? Because of what? Ion channels, ligand gated? Ligand gated ion channel? Voltage, very good. Because there are lots of these voltage gated sodium channels are expressed in this location. In the dendrites, we don't have many or much of the voltage gated sodium channels. This is why the signal decay, okay? The graded potential is generated because of the opening of the ligand gated ion channels. The voltage gated sodium channels or potassium channels, they are more concentrated in starting from the axon hill lock. And then we have them as well, in these particular locations, which are called nodes of Ranvier, okay, along the axon as well. And so starting from here is where we have enrichment of the voltage gated ion channels. And so this is why if the graded potential was big enough to depolarize the neuron in the axon hill lock, there is the likelihood that the voltage gated sodium channels would open, which will result in the generation of the action potentials. Anyone has a question? Yeah? You have a question? Sorry? How is the potential will decrease? What do you mean decrease? Because you mean in the cell body, the graded potential. So the graded potential is the result of the entry or influx of ions as a result of the ligand is binding to its receptor. And so depending on how many receptors are being open, so it will result in very small, depolarization of, small patches of the membrane. And as it travels, the cell body has some ions which are non-gated, and some of the ions will escape. okay? And so this will result in the decay of the signal that's being generated from the graded potential, okay? It's like a hose where there are holes in there. Yep.
Doctor?
Yep.
I have a question. When the ions reach the axon halo, does that mean it decreases the amount of impulses, or does it increase it? What happens there?
What do you mean? Can you elaborate?
When they reach to the axon halo,
Yes.
does that mean the impulse decreases in intensity because of the...
So the bottom line is when the graded potential is generated, this means that the membrane, so let's take sodium as an example. So when glutamate is bound to the MDA receptor in the dendrite here, okay, so let's take this. Sorry, just 1 second. So here we have the ligand-gated ion channels. Let's say these are the MDA receptors, right? And so glutamate is when it's bound to the ligand-gated ion channels, MDA, it will open. And when they are open, sodium will rush to the cell, right? And so when sodium gets into the cell, okay, it will generate a graded potential, but it's very small. And due to that this location doesn't have voltage-gated ion channels, this means that the depolarization will lose its strength by the time it reaches the axon hell lock. So if this neuron is receiving, sodium from multiple locations, let's say receiving sodium from this location and from this location as well, and so it will depolarize a larger area, and so the signal is likely to reach the axon hell lock to depolarize this area to the threshold, to make it to around a negative something millivolt, which we'll see in a second, okay? This is the threshold where the voltage-gated ion channels would open, resulting in an influx of sodium that will generate the action potential. Does this answer your question? Okay, okay, good. Now, the graded potential could be either excitatory or inhibitory. As I said, the entry of sodium would be excitatory, whereas the entry of chloride would make the membrane even, hyperpolarized. Okay, yep. Sorry? Yes. If it's strong enough. So as it travels, so you can see these as an example. If the graded potential was sub-threshold graded potential, by the time it reaches the axon hell lock, it wouldn't depolarize the membrane at that particular location to the threshold, which is negative 55 millivolt. And so if it doesn't take the membrane to that threshold, then the voltage-gated ion channels wouldn't be open. Remember that we said they have sensors, and they would open only when they reach the negative 55 millivolt. So if they don't reach that, then they wouldn't be open. And so this will not result in an action potential. It will lose, yes, it will lose its strength because it hasn't, opened the voltage-gated ion channels. Okay? Well, yeah, exactly. The message won't be transmitted. Yeah. Yes, as we will see in a second, we will learn about the ionic basis of the action potential. So this is just to show you the sequence of events, so from graded potential into an action potential. I'll take some questions afterwards because I may answer some of your questions along the way, okay? So from graded potential, if the graded potential was high enough to depolarize the axon hell lock, this will result in the generation of the action potential. And what is responsible for the generation of action potential is the opening of the voltage-gated channels. As we learned that the axon hell lock, we have an enrichment of the voltage-gated ion channels, like the voltage-gated sodium channels, as well as the voltage-gated potassium channels. And so as we learned in the previous lecture, that the voltage-gated sodium channels, they have two, they have two gates. There is the activation gate, okay, which they open the activation gate when they sense the change in the membrane potential to the threshold around negative 55 millivolt. Okay, so this is by being closed like this. When they sense the change in the membrane potential that reached the negative 55 millivolt, they would open to allow sodium to enter. When the membrane reaches around positive 35 millivolt, we said there is a second gate, which is the inactivation gate, right? And so when the membrane reaches positive 35 millivolt, the inactivation gate would be closed to prevent the entry of sodium. Is this all clear? All clear? Okay. Now, what are some of the properties of the action potential? So as we said, it is initiated by the depolarization of the membrane at the axon hillock, because in the axon hillock we start having the voltage-gated sodium channels, and so in that area, when it's depolarized to the negative 55 millivolt, the threshold, then there will be the generation of an action potential. It is all or none event, okay? What do we mean by all or none? So if the membrane at the axon hillock doesn't reach the threshold, there would be no generation of an action potential. If it reaches the threshold, then there will be the generation of an action potential. So either happen or it doesn't happen. There is nothing in between. So if the membrane reaches at the axon hillock the threshold, okay, so you can see here, this is the graded potential. If it reaches the membrane at the threshold, then there will be the generation of an action potential, regardless of how big the stimulus is, okay? The amplitude, the size of the action potential is always the same. It doesn't change. It doesn't get bigger or smaller. It's always the same size, the same amplitude. So when there is a strong stimulus, it will result in a higher frequency action potential. There will be many of them, okay? But the size, the amplitude of it doesn't change, okay? Is this clear? Only the frequency, when the stimulus is big, it will be translated as a higher or more frequency action potential, okay? So it has a constant amplitude, okay? Action potential don't summit, unlike the graded potential. We said they can, accumulate to produce a larger graded potential, okay? So the amplitude of the graded potential changes, okay? But with the action potential, it doesn't, okay? So information is coded by frequency, not amplitude. So as you can see here, once it reaches the threshold, it will happen, okay? So it either happen or it doesn't happen, okay? Is all clear? So the threshold is around positive 50 millivolt to the resting membrane potential, okay? So if the resting membrane is negative 70 millivolt, then the threshold would be around negative 55 millivolt, okay? All clear? Okay, so let's talk about the ionic basis of the action potential. What is it really that, how is the action potential develops, which you already guys have been exposed to during the previous lectures, but this will complete the whole story, okay? So as we said in the previous lectures that, the resting membrane potential is originates or, develops because the membrane has a higher permeability to potassium compared to sodium, right? There is a higher permeability to potassium, and this is why the resting membrane potential is closer to the equilibrium potential for potassium, right? So this change in the concentrations of ions across the membrane is really what contribute into the generation of the membrane potentials in general. But let's focus here on the resting membrane potential, and we know so far that the membrane potential is around negative 70 millivolt, and it is close to the equilibrium potential for potassium because of the membrane at rest. The membrane has a higher permeability to potassium than to any other ions, right? So let's take some basic electricity concepts here, which you're already probably exposed to. So we came across so many terminologies like the electrical potential or voltage. What do we mean by voltage? As we said before, like the battery, we said there is the cation, the cathode, the positive side of the battery, and here we have the negative side of the battery, right? And so the separation of the charge by concentrating, or the force that we, creating on the electrons on one side, it creates a voltage, okay? And this can be measured in a voltage and given, the V, as you can see here. And so once we connect the battery, the two sides, the anode with the cathode, the electrons will rush to go to the cathode side, isn't it? And so the movement of the electrons in the wire that we connected is what we call current, okay? And current is measured in amperes, and it is the movement of the charge. And current is denoted as I, okay? How easy it is for the ions or the charges to move. If the wire was small, okay, or the diameter of the wire, if it was small, there will be higher resistance. The conductance, or how easy it is for the current to move, would be reduced. Whereas if the wire was big, then the electrons will move easily, isn't it? And so how easy it is for the electrons to move is described as conductance, okay? And opposite to it is resistance. So when the conductance is high, it means there is a lower resistance. When the conductance is low, it means that there is a higher resistance. Is this all clear? Okay, so let's take this as an example. So there is a law which is called Ohm's law, which states that current, okay, equals voltage times conductance. So what does this mean? It means that when there is a high voltage and a high conductance, this will result in a higher current. Is this all clear? So let's take this as an example, this water tank. So this water tank, the force that we are creating on the water tank by making it up high, okay, this represent voltage. So let's take this example and then I will answer your question. So this water tank here is being put high, right? And so there is a pressure on water to move down, right? So this can be, representing voltage. Now you can see here we have an opening, okay, where, water, the flow of water, in this example can represent current, okay? And so the size of the pipe or the opening would represent conductance or resistance. So if the size of the pipe was big, okay, this means that there will be a increased conductance and lower resistance. But if it was, very narrow, this means that the resistance is gonna be very high and the conductance would be low. So let's take this here as an example where the voltage is high, so this number would be high, right? And also we have the size of the diameter here is also high, so the G, the conductance is gonna be high. And so when we multiply the numbers, the amount of current that will flow is gonna be big, right? Whereas in this case here, in this second example, the voltage is high, same voltage as this one, but the size of the diameter is low. And so conductance would be low, okay? And this will result in a smaller amount of current, okay? Is this all clear? Is this all clear? So the second one here, you can see that the size of the diameter is big. And so this means that the conductance is high. Okay, it is very easy for the water to move. And so this will result in a larger current, okay? Whereas here, the size of the diameter is low, which means that the conductance is low, and this will result in a smaller current, a smaller flow of water, okay? So same thing applies to the neurons or excitable cells, where current, okay, the amount of ions would flow is equal to conductance. Conductance of ions is the opening of the channels. When we have so many of the voltage-gated ion channels are open, this will result in a higher current, okay? And the Vm minus the equilibrium of the ion, you guys remember this? This is the driving force, okay? And so when the driving force is high, okay, for that ion to move, and when the conductance is high, this means that the current, the amount of ions that the amount of the ion will flow is going to be large. While if the conductance, if we have so many of the channels that are open, but there is no driving force, this means that the ions wouldn't move, okay? Let's take this as an example and you will understand this formula very well. So let's take this cell, hypothetical cell, and let's assume that the potassium is concentrated 20-fold inside. So we have a high concentrations of potassium inside and low outside, okay? Similarly with sodiums, it would be, high outside compared to inside, right? Now, let's take these hypothetical numbers that the equilibrium potential for potassium is negative 80 millivolt, okay? And the equilibrium potential for sodium is positive 62 millivolt, okay? We are good? We are good, right? And the membrane potential in this cell is 0 millivolt, okay? Now, given these values that the equilibrium potential for potassium is negative 80 millivolt and the equilibrium potential for sodium is 62 millivolt, okay? This means that there is a huge driving force if we open the channels for either ions to move, isn't it? Because, if we subtract the membrane potential from the ion of interest, it will give us the number, the driving force. So there is a huge driving force for either ions to move across the membrane. However, you can see here that the GK, this means that the conductance for potassium is equal to 0, right? And so the amount of potassium that would move is gonna be 0. Why is that? Because of the closed channels, right? All the channels are closed, so conductance is equal to 0. And so if we fill in the numbers here, okay, we know that there is a huge driving force for potassium, but the conductance is 0. And so this will result in no movement of potassium in this hypothetical case, where all the channels are closed. However, if I insert some potassium channels in here and potassium starts moving, okay, then we have a conductance that is more than 0. This will result in a current, right? So potassium will move, okay? While in here, once this cell reaches the equilibrium potential for potassium, so the membrane potential is now equals to negative 80 millivolt. Now the ionic driving force for potassium is equal to the membrane potential. So when it's equal to the equilibrium potential for potassium, this means there would be no movement of the potassium, right? And so although conductance is high, but there is no driving force for the potassium to move. And so in this case, this will result in no movement of potassium. Is this all clear? Yep. Huh? Conductance is how easy it is for the ions to move. Like we said in the example, Conductance here is showing by the size of the diameter. When the diameter of the pipe here is big, this means is the conductance is high. The water will flow. And in terms of ions is the ion channels. When they are open, this means that there is high conductance. When the ionic driving force is high and conductance is high, the channels are being open. This will result in the movement of the ions. Let me take questions afterwards. I just want to repeat the thing. Okay. Which one? Which one? In here, this slide? Okay, this one here? Okay. So here is conductance is equal to 0. No channels are being open, right? So although we have the, for example, here in potassium, there is a huge driving force because 0, okay, let me do this. So the ionic driving force, the way you calculate it, is 0 minus become positive 80 millivolt, right? And so there is positive 80 millivolt, like we learned before, right? So there is an ionic driving force of positive 80 millivolt, which means when we see positive for a cation, it means that the movement is going to be inward or outward? Outward, right? So this means there is an ionic driving force, right? But the conductance is 0 because no channels are open. So it doesn't matter. So as you can see here, with this formula, there will be only current when the conductance is high as well as the ionic driving force is high. So if either is 0, then this will result in no current. And so in the first example, we have a huge ionic driving force for potassium, but no channels are open, right? And so there will be no movement of potassium. Now in the second example, now we have a conductance of more than 0 because we have the channels are being open. So we have both high conductance as well as high ionic driving force, which will result in the movement of potassium to the outside, right? And in the third example, the ionic driving force is 0 because if you calculate the ionic driving force, now the membrane is at negative 80 millivolt, right? And because it has reached the equilibrium potential for potassium, and so negative would be positive 80, which is the equilibrium potential for potassium, and so the ionic driving force would be 0, right? And so when the ionic driving force is 0, although all the channels are open, like the conductance is here in this example more than 0, but there is no ionic driving force for the ion to move. And so there will be no current that will be moving. There would be no movement of potassium. So ions will move as long as there is high conductance, there is conductance, as well as there is an ionic driving force, okay? This is the bottom line. Is this all clear? Clear? Okay, so this will, this just explain what I said. You can read it on your own. And so, as we said, that ions will only move when there is conductance as well as there is an ionic driving force. And so this is what happens in an action potential. Now, at rest, we know that there is high permeability or higher conductance to potassium, and this is why the resting membrane potential is closer to the equilibrium potential for potassium. Now, when the membrane reaches a threshold, we have the voltage-gated sodium channels are being open, and so there is high conductance for sodium, and there is a huge ionic driving force for sodium to move to the inside of the cell. And so this will result in the depolarization of the membrane, okay? Where the membrane will go towards, the sodium will move to the inside to take the membrane closer to the equilibrium potential for sodium. You remember what's the equilibrium potential for sodium? Positive 70, right? Sorry? plus 70 millivolt. That's the equilibrium potential for sodium. And so when we have the voltage-gated sodium channels are being open, right? Now sodium, there is a huge ionic driving force for sodium to go from outside to the inside to make the membrane go towards its equilibrium potential, right? And so we have the membrane now is being depolarized to reach around positive 35 millivolt. And because we know that the voltage-gated sodium channels have an inactivation gate, which will close at in that particular voltage. So the closer of the sodium voltage-gated channels and the opening of the potassium voltage-gated channels will result in the repolarization of the membrane towards its resting state, okay? So the bottom line is what is responsible for the upstroke of the membrane potential, the slope that's going up, is the high conductance to sodium. And what is responsible for the downstroke of the action potential is the high conductance to potassium. So here we have few terminologies that you need to learn about action potential. So depolarization, as we said, is to bring the membrane, to make the membrane have a more or less negative membrane potential, right? Whereas hyperpolarization is to make the membrane has a more negative voltage, okay? Whereas repolarization is to bring the membrane down to its resting membrane potential, and the overshoot is this part of the action potential, which is above 0 millivolt, okay? Is this all clear? Okay, so let's review everything very quickly with the action potential. So at rest is the membrane is at negative 70 millivolt, and this is due to high permeability of the membrane to the potassium, right? And so this is why the membrane at rest is closer to the equilibrium potential for potassium. Now, when there is a graded potential, there is the flow of sodium that's now creating some, depolarization, which has reached the threshold, has reached the axon Hillock to depolarize the membrane to threshold of negative 55, negative 50 in some neurons. This will open which channels? Voltage-gated sodium channels, right? Because the voltage-gated sodium channels, they have a sensor, and they would open their channels when when the membrane reaches negative 50 or 50 millivolt, right? Now, the opening of the voltage-gated sodium channels will result in the influx of sodium to the cell. Why is that? Why is that? Because there is a huge ionic driving force for sodium to move from outside to the inside, right? In order to take the membrane towards its equilibrium potential, which is the around positive 70 millivolt, isn't it? You guys are with me? Yeah, so sodium will move to the inside, okay, because there is a huge ionic driving force, and it is in its interest to take the membrane towards its equilibrium potential. But only, as you can see here, the membrane will reach, when it reaches around positive 30 millivolt, what will happen? The inactivation gate, right? The inactivation gate would be closed, okay? And now we have the voltage-gated potassium channels are opened. They sense this change. So when the membrane reaches around positive 30 millivolt, we have the activation of the voltage-gated potassium channels and the closure of the inactivation gate of the voltage-gated sodium channels. Now, why potassium would be leaving the cell in the repolarization? So here is the upstroke, where the membrane is being depolarized. It's going more toward the less negative, more positive values. This is where the membrane is being repolarized to the resting state, Why potassium, is leaving the cell during repolarization? Why is that? Yep. Okay, because there is a huge ionic driving force for potassium. At this state, if we calculate the ionic driving force, so it is 30 millivolt, right? The membrane potential is positive 30 at this particular state, and the equilibrium potential for potassium is going to be around positive 80, because we know minus minus is positive. So it will be around 120 millivolt, right? So there is a huge ionic driving force for potassium to leave the cell, isn't it? Because it wants the membrane to reach its equilibrium potential. Is that clear? And so this is what's responsible for repolarization, is the closer, because the inactivation gate of the voltage-gated sodium channels are closed, and now we have the opening of the voltage-gated potassium channels, and there is a huge ionic driving force for potassium to leave the cell. Okay, so that's repolarization. And as you notice here, that here is the resting state, but the repolarization doesn't stop here. Why is that? Why it's even further hyperpolarized? Sorry? Again? No, because, yep. They have what? Why the membrane is even lower than the resting membrane potential? Why is that? Yeah? Very good. Because the equilibrium potential for potassium is around negative 80 millivolt, right? It's around negative 80 millivolt is the equilibrium potential for potassium. And because these channels, the voltage-gated potassium channels, remain open even further, so there is conductance for potassium. And so even when it reaches the resting membrane, still potassium is going out wants to reach the equilibrium potential for potassium. And so once they are closed, and the active pump will restore the membrane to the resting state. Okay, is this all clear? So now what you need to know is that there are drugs which act on these voltage-gated channels. For example, we know that tetrodotoxin, TTX, which is, found in Japanese fish, is known to block the voltage-gated sodium channels. And so if you eat a lot of these types of fish, this will result in paralysis, okay? Because, once you are blocking the voltage-gated sodium channels, this will result in the prevention of the generation of the action potential, isn't it? Okay? There are other drugs as well, like, this one here, TEA, which is known to block the voltage-gated potassium channels. And this is how scientists actually study the action potential, by blocking the different channels and measuring the, the current of the ions. Okay, yes? Maybe, I'll have to check, maybe. Okay, so you guys are all good? Okay, now, there is something called refractory period, where there is the absolute refractory period, where no matter what, if there was a second stimulus, okay, there would be no generation of an action potential. So this period in an action potential is called the absolute refractory period, okay? And this is caused by the inactivation gate of the sodium channels. Remember the inactivation gate of the sodium channel, which you close in here, okay? So these gates, the inactivation gate, would not be open, okay, until the membrane is near, its resting state. So during this period of time, no matter what the next stimulus, how big it is, there would be no generation of an action potential, like the flush in a toilet. If you click, there will be flush. If you click right away, there wouldn't be a second flush, isn't it? Right? So it has to relax and then you can flush again. Sorry to bring this example, but... and so there is also a relative refractory period. So the relative refractory period is this period when the membrane is at even higher hyperpolarized state than the resting membrane potential. This is the resting membrane potential in blue. And as you can see that the membrane potential is even more hyperpolarized than the resting membrane potential. This is the relative refractory period. During the relative refractory period, you can, the neuron can generate a second action potential, but the stimulus has to be very big in order to bring the membrane to threshold, because the threshold is even more far, as you can see. Whereas when the resting state, this is how far it is from the resting state. Okay? Is this all clear? Okay, good. This is just explaining what I said. And so what we described is the typical of an action potential in neurons. Other excitable cells like cardiac muscles, they have similar type of action potential. But what you need to know in here is that there are different ion channels that that are in action in the cardiac muscle cells. As you can see here, the depolarization or the upstroke of the action potential similarly is the result of the rapid influx of sodium. And here, as you can see, that the outward movement of potassium is responsible for the action potential to to reach 0 millivolt, but now we have a plateau. And what's responsible for the plateau of the action potential in the cardiac muscle cell is the entry of calcium, because we have calcium entering through calcium voltage-gated channels, and there is the exit of potassium, right? And so because of this opposite direction of the ionic movement, this results in the plateau of the action potential. Is this all clear? Okay, very good. This is the end of the lecture. I think we went over. But any questions?